Q is conserved. Conserved is a physics term for saying does not change with time. Electrical charge may migrate from A to B or from B to A, but when you add up the total charge, the charge of the final products is always equal to the charge of the incoming products. Charge conservation needs to be amended with one extra term, one extra qualification. It's called local. Suppose we say that the number of students in a classroom is conserved. So that means you count the number of students anytime, you gotta get the same number. Let's assume that at one instant, one of the students disappears and reappears somewhere else in the classroom. This is consistent with the conservation of the number of students because the number of students didn't change. Let's imagine the same situation but with charges. Let's imagine a proton disappears somewhere and a positron appears somewhere else. The number of charges is still conserved. But that is not a local conservation of charge because it disappears in one part of the world and then appears somewhere else, and it's not even a meaningful law to have in the presence of special relativity. So why is that? Because it's not simultaneous in every frame of reference. We know from the special theory of relativity that if we have two events that are simultaneous in a frame of reference, if we see those same two events from a moving train, they will not be simultaneous. So from another frame of reference, the charge could disappear and then after a period of time reappear somewhere else. Or the appearance could take place before the destruction, so suddenly you've got two charges. Conservation of charge, which is conserved non-locally, cannot have any significance except for one frame of reference. If you want to make laws that works for everybody, and if you believe that observers are all equivalent, then charge must be conserved locally. So electrical charge is conserved and it is local. It is locally conserved. Also, stuff doesn't just disappear. Stuff move around. You can keep track of it, and if you add it up, you get the same number. Q is quantized, which means that any charge, any electrical charge that we run into does not take a continuum of possible values. Electrical charge is not continuous. Every charge that we have ever seen in the world is a multiple of a certain basic unit of charge, which is 1.6 times 10 to the power negative 19 coulombs. Every charge is either that or a multiple of that, a positive multiple or a negative multiple. What is actually going on microscopically? We know that everything is made up of atoms, and the atom has a nucleus. We got protons and neutrons, and we have the electrons, which are the guys running around. Actually, this picture is only good for this purpose. And for neutron, it's 0. The charge of a neutron is 0. The charge of an electron is a negative 1.6 times 10 to the power negative 19 coulombs, and the charge of a proton is 1.6 times 10 to the power negative 19. It's just the positive multiple of the charge of an electron. Every electron in the universe has exactly the same mass and exactly the same charge. If it had a different charge or a different mass, we would actually call it something else. All electrons in the universe are identical, and all protons of the universe are identical. Quantum field theory gives a reason why all electrons are identical and why all protons are identical. Actually, if they were any different, any different, things would be very difficult for us because we wouldn't be able to make any predictions. Why is the charge of an electron is equal and opposite the charge of a proton? Their masses are different and their other interactions are different. That's actually what makes an atom electrically neutral.